Okay, so here's a wild idea. What if you could actually hear a blackout coming? I don't mean when the lights start to flicker. I mean hours, maybe even days ahead of time. Well, that's the core idea behind this new technology called the Coherence Engine. And, it could completely change how we manage our power grids.
Just think about that for a second. Right now, we usually only find out there's a major grid problem when some alarm finally goes off, or worse, when the power's already out. It's totally reactive. But what if the grid was humming along like this incredibly complex machine? And what if we could learn to hear it starting to drift just a little bit out of tune, giving us a heads up long before it ever breaks down? To really get why this is such a game changer, we have to talk about a hidden problem that's growing in our grids. See, as we add more renewables like solar and wind, our power systems are getting way more complex. And that complexity, it's creating all these brand new, totally invisible challenges. Here's a pretty cool way to think about it. Imagine the power grid as a giant, perfectly synchronized symphony orchestra. For decades, it was made up of a few big, predictable instruments. Pretty simple. But now, with all the renewables coming online, we've added hundreds, even thousands of new, smaller musicians. They're called inverters, and they're what bring all that solar and wind power into the mix. The problem is, it's suddenly a lot harder to keep everyone playing perfectly in time. And this is the most important part. Failures in these new modern grids don't usually start with some big, loud mistake. Nope, they start as a slow, quiet drift. All these little controllers start interacting in weird ways. Their timing, what engineers call phase locking, it gets a little bit off, and the whole system loses its natural ability to absorb shocks. This drift is the real danger, and it's happening long before any of our traditional alarms would ever pick it up. So, if the problem is this quiet drift, you can't just solve it with a louder alarm, right? That won't work. You need a completely new way of looking at the system's health. You need something that can listen to the entire orchestra, not just one out-of-tune violin. And so, the solution is basically to give our orchestra a conductor. That's exactly what the Coherence Engine is designed to be. It's this monitoring layer that isn't listening for a single wrong note. Instead, it's sensing the relationships between all the different players. It can literally tell when one section starts to drift, even slightly, out of sync with another one, giving the grid operators this clear early warning that the harmony is starting to break down.
So how does this thing actually work? I mean, how do you take all this ridiculously complex grid data and turn it into a simple, uh-oh, look at this kind of insight? Well, it's a really smart three-step process that basically turns information they already have into a totally new kind of intelligence.
Okay, first the inputs. And here's the best part. The system doesn't need a bunch of new, expensive sensors. It just uses the data that grid operators already have. Stuff like their controller logs, data from the inverters, standard SCADA measurements. Then comes the transformation step, and this is where the magic happens. It analyzes the relationships between all those signals over time. And finally, the outputs are incredibly clear and useful. You get a simple stability score, you get early warning flags, and maybe most powerful of all, you get something called a coupling map that shows you exactly which components are causing the instability.
Now, a new technology like this, it sounds great in theory, but you have to ask, how do you prove it actually works in the real world without starting some massive multi-year project? The answer, it turns out, is a super fast, really focused proof of concept.
And when I say fast, I mean really fast. In just 4 to 8 weeks, a team can go from just setting goals all the way to validating the system against actual past grid events. Just imagine that. By week 5, you're already figuring out exactly how much earlier you would have known about a problem compared to the old systems. It makes the technology feel real, and it proves the value almost immediately. And success here isn't some vague, fuzzy idea. It's measured against really clear, objective things. Does it give you more lead time before an event than you had before? Simple, yes or no. Can it clearly tell the difference between a grid that's stable and one that's under stress? And maybe most importantly, is the information it gives you actually actionable? That coupling map has to point operators to the real source of the problem, so they know exactly what they need to go and fix.
So when you put all of this together, what you're really looking at is a fundamental shift in how we manage our power grids. It's all about moving away from being reactive and towards being proactive. It's about, well, building a truly smarter grid. The change is pretty simple, but it's also profound. In the past, we were reactive, right? We waited for a single thing, like voltage or frequency, to cross some big red line. That's basically waiting for the smoke alarm to go off. Now the approach is proactive. By analyzing the relationships between all the signals, we can spot that subtle drift that leads to failure. It's the difference between hearing a smoke alarm and smelling the smoke long before there's ever a fire.
It really all comes down to this one simple insight. Failures often emerge as drift and unstable coupling before any of the alarms go off. The huge, catastrophic events we're all worried about, they don't just appear out of thin air. They start small as this gradual uncoupling of the system. And if you can recognize that drift early, that's the first step to preventing the disaster entirely.
So this brings us to a final, really powerful question. This technology is all about teaching our electrical grids to listen to their own health in a totally new way. And if we can do that for something as complex as a power grid, what other huge, complicated systems could we do this for? What other invisible problems in our supply chains and finance, maybe even in our own health, could we solve just by learning how to listen for the drift before the failure?